Professor Reddy and distinguished guests, I'm really sorry that because of a leg accident at the end of September, I cannot be here and meet you all in person. I'm honored to be in front of such a group of famous and clever people. In particular, I'm missing the people I was lucky to work with and to whom I owe much. My time at CMU Speech Lab, 14 happy years, has been, work-wise, the most fulfilling and interesting of my life. I've learned what I never would have learned otherwise. Let me just spend less than a minute to tell you how I happened to get there. My interest has always been in multiple instruction, multiple data, multiprocessors. Sorry for the ancient definition. These kind of multiprocessors are just the opposite of vector machine and GPUs, as you all know. So I applied and got a grant to visit what I consider the land of multiprocessors, thanks to projects like C.MMP and CMStar. It just happened that I arrived at the wrong time, and the PI of those projects was visiting another university. I was an orphan. The space manager parked me in the smallest room of Wynne Hall with hundreds of blue research reports. After much reading, I found one that really stimulated my curiosity. It was by a guy called Ray Reddy and had the AI keyword in the title, a term I mistrusted. I went to visit him, and Beverly, his secretary at the time, was shocked. "Raj, not Ray," she said. I went in and told him I was interested in multiprocessors and parallelism, but not AI. Well, I do not recall why I came out of the office as a speech person. So I found myself studying HARPy, the speech recognition system. One of the first things I learned was that the task required a hefty chunk of signal processing. Signal processing was by its nature a computation that could easily be done on vector machines. The problem was that in 1976 there were only big and expensive machines that could do it in real time, and one of the goals was to build a real-time, small and inexpensive system, and correct, of course. This problem was solved a few years later with the production of fast floating point coprocessors, like the Intel 8087. And later, even the coprocessors were incorporated in the main processor. In the meantime, we tried to work around the problem by programming existing microprocessors at the lowest level. For this bad idea, I gained the perpetual hate of Philaliva. But the real problem was the search, because of its unpredictable behavior. Please bear in mind that this is a historical and partial reconstruction of what we did roughly in the 1980s, early 1980s. After that, much has happened that has led to much better results. Search was a different story. The program behavior was dependent on input data, and in a parallel machine, the load had to be controlled dynamically. Moreover, operations were performed to a large database and had to be synchronized. With the high granularity decomposition of the search task, delay could slow down the whole computation. Some processors would have a small load and others a high load. But with a low granularity decomposition at the single node expansion, the synchronization time was critical. Over the years, keeping into account the rapid change of hardware performance, we investigated many avenues with good and less good results. I will only mention 3 of these avenues, 2 good and 1 bad. The first one was a careful rewriting of the search software. We started from a version of Harpy written mostly by Bruce Larry, the best one at the time and highly optimized, and rewrote a few key parts as indicated by careful analysis. It was less than a day of programming. The search became 10 times faster, and the speed up remained when the same software restructuring was ported from the C language version to a PDP-11 on a PDP-11 to a C language version on a KL10. Therefore, it was a result independent of language, compiler, and hardware architecture. The problem was that the speed up was close to impossible to improve with this method. A factor of 10 was too little for large tasks, although it was a very good result. The second effort I want to mention was done with Ravi Shankar Moser, then a PhD student. As I said before, the delay paid by the search task when accessing a large set of data in an unpredictable way was offsetting the speech gain by having multiple processors. For this reason, we built a machine that used a number of powerful microprocessors connected to a large shared memory by a memory processor and a message network, implemented thanks to a custom VLSI message switch made available by DARPA. The hardware memory model was weakly coherent, meaning that often the memory did not contain the correct data. But, of course, if this data was required, the memory would always return the correct answer to the software. The memory processor and the network interconnection guaranteed coherence and low synchronization delays. The system was simulated and showed promising performance. It was 16 times faster than real time with 8 processors. That is, it could process 16 different utterances at the same time and still get all the answers in real time. Encouraged, we built a prototype with 2 processors. Unfortunately, we never got it to a level of reliability that would permit conclusive measurements. This is my fault because we built the system from scratch instead of using commercial processor boards. To be remembered. The third avenue I would like to mention is a simple approach that was also our most successful at the time. We concentrated on a few kernel operations of the search loop of the Sphinx system by Kai-Fu Lee, a very improved version of the Harpy system, but with a search behavior very similar to the old Harpy, and implemented them on a very fast, for the time, microprocessor, the YTEC 8032. There were only 4 processors and they were connected to a bus hosted by a general processor machine. The system was built together with Lawrence Butcher and was called Beam. Sphinx was publicly demonstrated in a large lecture hall, passing the microphone from person to person. Sphinx was running on Beam, hosted by a Sun system. The great success of the system had to do with a very low error rate in the context of a speaker-independent continuous speaking task. But would it have been so impressive if each utterance had required 1 minute to be recognized? I do not think so. Frankly, it was the first time that I believed speech recognition could be used for real. I would attempt no presentation in Raji's presence without a lessons learned summary. The lessons were many, too many to mention here. If we restrict ourselves to the task of speeding up speech recognition systems, here they are. First, program-level multiprocessing has a very limited speed up. Second, do not forget memory access and synchronization delays. Third, task-oriented hardware is a win, but it is very time-consuming to build. 4, never build too complex a prototype. 5, Never underestimate the improvements of hardware components. Your research problem might disappear. We all know that now multi-threaded processors and GPUs can run any of these tasks as fast and as cheap as needed. My time at the CMU Speech Lab, 14 years, has been work-wise the most fulfilling and interesting in all my life. I left Pittsburgh only because I needed to be close to my parents, and I do not regret that. At CMU, I've learned what I would have never have learned anywhere else on speech recognition and life. Last but not least, I would like to deeply thank Professor Reddy because he has been an exceptional mentor and friend. Thanks for everything, Raj.